Hello and welcome to 4.4. Today we'll be looking at properties of definite integrals. So one of the things we're looking at is theorem 5. We could have different sections of area that we could split apart and add multiple integrals together. Okay, so for example, we could have a range that would be from C to B and another range from B to A. We could add the two areas together. This works nicely when we have piecewise functions. For example, in number 1 here, we have a piecewise function where part of the function is x squared for when x is greater than or equal to 3. So we have a curve. And then the other part is a horizontal line, f of x equals 9, when x is less than 3. And important to note that we're going from -4 to +5, so that's why we're limited between these two areas. Okay, so we could split this apart into two sections of area, two integrals. Okay, the first one we could do, well, overall we're going to still do from 5 to -4. Okay, and then we'll calculate this as the first piece would be the rectangle from 3 to -4. Plus the integral from 5 to 3. Okay, so for the first piece, our function was 9 from 3 to -4. 9 dx. And then we have integral from 5 to 3 of x squared dx. Okay, so the integral of 9 would be 9x. So this would be 9x. And then we would have, for x squared, we would have 1/3 x cubed. And we would integrate and evaluate 5 to 3. Okay, so for 9x, we could have, we'll plug it in, we could do like this. We could have 3 minus -4. So 9 times 7. Right? 3 minus -4 is a +7. For the 1/3 x cubed, we would have 1/3 of 5 cubed. 1/3 of 5 cubed minus 1/3 of 3 cubed. Okay, so here we end up with 63, and then here we have, so we have 125 over 3, which we have as 41 2/3. This one will be 3 cubed, which is 27, 1/3 of 27, which would be 9. Okay, so we have 63 plus 41 2/3 minus 9, so that gives us 95 2/3. Okay, let's take a look at our next one. We have integral 4 to -3 of absolute value of x. Okay, one thing we have to note with absolute value of x remember, absolute value of x, if we graphed it, absolute value of x, it's really a piecewise function. Absolute value of x is this V shape, where the vertex would be coming out of the origin. Okay, so basically you have this piece is like, the right side is like x, f of x equals x. And then the left side is kind of like f of x equals negative x. Okay, so for us to be able to effectively do this, we will take, so it's from 4 to negative 3. So let's say this is 4, and then negative 3. So we're basically finding the area underneath like this. Okay, so we'll split this up into two regions. For the 4 to 0, because the 0 is the changeover point. So we would have integral from 4 to 0 of x plus integral from 0 to negative 3 of negative x. And now we'll integrate both of these. Okay, so when we integrate x, we end up with x squared, 1/2 x squared. And then we'll go 4 to 0. And then for negative x, we would have negative 1/2 x squared. And we would go from 0 to negative 3. Okay, so now we plug in. We plug in 4. So we have 1/2 of 4 squared minus 1/2 of 0 squared. So that gives us 4 squared is 16. Half of that is 8 minus 0 squared is 0. Plus, and then we have negative 1/2 x squared. So that means we have negative 1/2 of 0 squared minus negative 1/2 of negative 3 squared. So this part gives us 0, and then this part is 3 squared is 9 halves, and then minus a negative is plus, so we got 9 halves. Okay, so we have, here we have 16 halves. 8, we could make it into halves by saying 16 halves plus 9 halves, which ends up giving us 25 halves. Okay. Alright, next is the topic of area between curves. Right? So if we have a region bounded by two graphs, how do we find the area between the two curves? Okay. So the typical method for this is we take the area underneath the curve of the top function. Like in this diagram, we have the top function as f of x. We take the whole area underneath, and then we subtract away the area that would have been under the g of x, the bottom function. Okay, so you have to be able to identify top function and bottom function. And so we would have the same definite integral, and we would just put f of x minus g of x, simplify as much as possible, and then we would integrate that and then evaluate the bounds. Okay. So for this one, it says find the area of the region bounded by the graphs of f of x equals 2x plus 1 and g of x equals x squared plus 1. Okay. So now, don't always assume f of x is the top and g of x is the bottom. Sometimes they flip it on you guys. So you always want to get a good sense of the graph in the beginning, so you know which one's top, which one's bottom. Okay. So let me draw, because I think I have an idea, and I think we should all have an idea. F of x is a linear function. We could draw a quick graph of it here. So f of x is 2x plus 1, so that means we start at plus 1, and the slope is 2, which is 2 over 1. So go up 2, 1, 2, over 1, 1, 2, over 1. And we would keep going like that, 1, 2, over 1. So the line would look like this. For g of x is a parabola, x squared plus 1. So at plus 1, that's the y-intercept. So we would start at plus 1. And then we have x squared. So it's a typical x squared graph, but now everything is shifted up 1. Okay, so we have a... and if you're not sure, make a table. So we know at 0 we have 1. If we have 1, 1 squared is 1 plus 1, which is 2. At 2, 2 squared plus 1, 2 squared is 4, plus 1 is 5. Okay, so we have 0, 1, 1, 2, 2, 5, 2, 5 will be about there. And it would continue. At 3, if we kept going, 3 squared is 9 plus 1 is 10. So you see at 3 it would be like up here somewhere. Okay, so basically we're trying to figure out the region in between here. Okay, so it's important to note, top function happen to be the f of x. Okay, so that's our top function. Bottom function is the parabola, x squared plus 1. Okay, now it's also important for us to figure out the bounds. They didn't tell us any bounds, so we need to figure out, well, we know that we could go back to 0, because they both have a starting point at 0. Where do they intersect here? It looks like 2, but we could verify that. Okay, so let's verify it. We want to see where they meet up, where the two functions are the same. So we'll set those equal to each other. So we'll say f of x, we want to figure out where it's equal to g of x. So 2x plus 1 equals x squared plus 1. Okay, so we end up with, what do we have? We can set, we can move stuff over to one side. This is going to look like a quadratic because we have an x squared term, we have an x term. If I subtract 2x and if I subtract 1, and subtract 2x and subtract 1, that gives me 0 equals x squared minus 2x, and the 1 minus 1 cancel. Okay, so how do I solve for x here? Well, I can factor out an x. So I left with x times x minus 2. And now set each of these equal to 0. So I have x equals 0, and then x minus 2 equals 0, which means x equals 2. And that confirms the first one was x equals 0, which we knew about already. And the second one is x equals 2. So we're looking for between 2 and 0. Okay, so let's do the integral from 2 to 0. And we'll do f of x minus g of x with respect to x. Okay, so remember, top function was f of x, so 2x plus 1 minus bottom function, which was x squared plus 1. And because you're subtracting the whole function, put that second part in parentheses. Okay, so, and now we simplify. Okay, so we have the plus 1 and the minus 1, so that means we're left with 2x minus x squared. Okay, so that's something we could easily integrate. Right? Integral of 2x would be x squared minus integral of x squared will be 1/3 x cubed and 2 to 0. Okay, and now let's plug in 2. So we have 2 squared minus 1/3 times 2 cubed minus 0 squared minus 1/3 times 0 cubed. The second piece will not matter because they're both zeros. So we end up with 4 minus 8. 2/3 is 2 to the third is 8. So 4 minus 8/3. So that means we have 12/3 minus 8/3, which is 4/3. Okay, and that would be it. That's a typical problem where we have to find the area between two curves. Okay. Next application would be the average value of a continuous function. So this formula gives us the average value of a function on a closed interval. Okay, so it's your typical integration piece with this added fraction in the front. This added fraction gives us the average together with this fraction. This equation gives us the average of a function on a closed interval. Okay, so it says find the average value of f of x equals x squared over the interval 0 to 2. Okay, so x squared, we typically know what x squared looks like. It's a function, that's a parabola. And we go from 0 to 2. So let's say 2 is here. From 0 to 2. So we want to figure out where is the average value of this function. Okay, so first let's figure out 1 over b minus a. So we're going to do, remember, the first value in the interval is a, second value in the interval is b. So we have 1 over 2 minus 0 times the integral of 2 to 0 of our function x squared dx. So 2 minus 0 is 2, so we have 1/2. We can integrate this. X squared would be 1/3 x cubed. So we'll do is we'll say 1/3 x cubed. We have to evaluate the bounds. Okay, so that means we have 1/2. Plug in 2, so 1/3 times 2 cubed minus 1/3 times 0 cubed. Well, 0 cubed is 0, so that's gone. 2 cubed is 8. 1/3 of 8 is 8/3. So we have 1/2 times 8/3. We could do a little cross canceling. 2 divided by 2 is 1. 8 divided by 2 is 4. So 4/3. Okay, so that means the average value of this function between 0 to 2 would be 4/3. Okay. Let's do an application of this. It says Rico's speed in miles per hour t minutes after entering the freeway is given by this function. Okay, where t is less than or equal to 30. From 5 minutes after entering the freeway to 25 minutes after doing so, what was Rico's average speed? And then a follow-up question, how far does he travel over that time interval? Okay, so to help us out then, we're going to, well, we're asked about average speed, so we're going to figure out the average value. Right, so we're going to do, the interval is from 5 to 25. So 5 to 25. So that means we could do 1 over 25 minus 5. And then we're going to take the integral from 25 to 5. And we'll put our function inside the integrand. So we have negative 1 over 200 t cubed plus 3/20 t squared minus 3/8 t plus 60. And then this would all be with respect to t, dt. So we have 1 over 20, integral 25 to 5. Integrate all these. Actually, we don't need the integral because we're going to integrate right away. This is an easy function to integrate. So we have negative 1 over 800 t to the 4th plus 1/20 t cubed minus 3/16 t squared plus 60 t. And then we'll plug in 25 to 5. Okay, so we'll have 1/20. And then we plug in 25 for all the t's for the first step. So negative 1 over 800 times 25 to the 4th plus 1 over 20 times 25 to the 3rd minus 3/16 times 25 squared plus 60 times 25. Okay, we'll put this in parentheses. Okay, minus, and then we're going to do the same thing now with the 5. So negative 1 over 800 times 5 to the 4th plus 1 over 20 times 5 cubed minus 3/16 times 5 squared plus 60 times 5. Okay, so the rest is going to be arithmetic. When you figure this all out, you'll have 1 over 20, and you'll have 53,625 over 32 minus 9,625 over 32, and you'll end up with 68.75 miles per hour. Okay, so that's the first part of the question. And then they want to know the distance traveled over that interval. Well, keep in mind 20 minutes is equal to 1/3 of an hour. Right? If we just take 20 divided by 60 minutes in 1 hour, right, that's equal to 1/3 of an hour. So that means if we're finding distance, remember distance equals rate times time. So our rate is the 68.75 miles per hour. Our time is the 1/3 hours. So to get the distance, we would do rate times time, so 68.75 times 1/3 of an hour. Okay, multiply that together and we would get 22 and 11/12. So 11/12 .9, let's say 0.92. 22.92 miles will be the distance traveled. Okay, let's take a look at the next piece. 4.5, integration techniques, substitution. So in substitution, we're going to look at three major techniques, but overall, we're going to basically be doing chain rule with integration. Okay, so these are for our more complicated looking functions. But first of all, we're going to remind ourselves of some basic how do we take the derivative of certain functions. Okay, so these are just our typical integration. This is the power rule, right? If we're integrating u to the r, we add 1 to the exponent and we divide by that same exponent plus c. Integral of e to the u would be e to the u plus c, and integral of 1 over u du would be ln of the absolute value of u plus c. Okay, so these are some typical ones, right? So number one, it says find dy. Right, so remember back a few chapters we did separation of differentials, right? dy dx. So typically to get the derivative, we would say here we have dy dx equals derivative of x cubed would be 3x squared, and to get dy we multiply both sides by dx. Right, so we end up with dy equals 3x squared dx. Okay, for u to equal capital F of x equals x to the 2/3, we want to find du. Okay, so that means if u is equal to x to the 2/3, we would get du dx. Du dx would be 2/3 x, and then subtract 1. 2/3 minus 1 will be negative 1/3. Okay, so that means to get du would equal 2/3 x to negative 1/3 dx. Okay. Alright, so example 3, u equals ln x. Find du. So du dx would equal 1 over x. And then to get du, we would multiply both sides by dx. So 1 over x times dx. And sometimes we write this as, we put the dx on top, dx over x. Okay. For example 4, we have e to the x squared. Okay, so we got to do a little chain rule here. So if we have y equal to e to the x squared, dy dx would be, well, derivative of e to anything would be itself, right? So we e to the x squared, and then we have to multiply by the derivative of x squared. Derivative of x squared would be 2x. Okay, so we could put the 2x in front, 2x e to the x squared, and then we would multiply both sides by dx to get the dy. So dy equals 2x e to the x squared dx. Okay. Alright, let's take a look at example 5. Evaluate the integral. Okay, we have 3x squared times x cubed plus 1 raised to the 10th power dx. Okay, so the way that we work with this is we're going to use a technique called substitution. We have to figure out what is the thing that's really being integrated and what's the piece that's really the part of the chain rule. Because remember, there's an overall function that we need to integrate, and then there's a piece that we're keeping track of that's the kind of like the after part, like with the chain rule. Okay, so the major piece here really is we have this x cubed plus 1. That's really the major piece that's getting integrated here. And notice the 3x squared, that would be the derivative of x cubed. Okay, so the way we typically set this up is we say, we use a variable. Usually we use the variable u. We say u equals x cubed plus 1. And then we take the derivative of u, du dx would equal, now if we take the derivative here, we get 3x squared. And if we write it as differential, this would be du equals 3x squared dx. Okay, so now when we do the substitution technique, we literally are going to substitute. We say x cubed plus 1 equals u. So we're going to substitute the x cubed plus 1 with u. Okay, and then the 3x squared dx, notice the 3x squared dx is the du, and we have that here. The 3x squared dx, that is our du. Okay, so right now we have a u to the 10th, and then we have a du. And so it's this thing that we can now integrate. Okay, we have u to the 10th du. So when we integrate it, we get u to the 11th over 11. And then don't forget plus c. And so now how do we express this in terms of x? Well, we plug the u back in. You plug in the x cubed plus 1 back in. We could restate this by saying 1 over 11 1 over 11, and I plug back in for u x cubed plus 1 to the 11th plus c. And that would be the final answer. Okay, so this is called the substitution technique. Sometimes we call it u sub, but u substitution. Okay. Let's take a look at our next example. It says evaluate 2x dx over 1 plus x squared. So we want to think, okay, what could be our function for the u? Okay. Well, notice how 2x is the derivative of x squared. So that's always a good indication that the 1 plus x squared, that will be the u. Okay, so we'll say u equals 1 plus x squared. That means du would be 2x dx. Okay, so we have the 2x dx already there, so that's good. So if we use our u substitution, that means we have u on the bottom, and on the top we have du. Okay, so now remember, what does this remind us of? Right, where it's u on the bottom and du on the top. Okay, so this would be our ln. Right? That's how an ln typically works. If we took the derivative of a natural log, we have 1 over that function times the derivative, and the derivative we could put on the top. Okay, so we could say this is going to be ln of u plus c, and then we could just plug it back in and say this is ln of 1 plus x squared plus c. Okay, let's take a look at our next example. Evaluate integral of 2x dx over 1 plus x squared, which is squared. Okay, so it looks like we could use 1 plus x squared again. So u equals 1 plus x squared, and that means du would equal 2x dx. So luckily for us, the 2x dx is there. Okay, so let's substitute into this. So we have integral of, on the top we have du, on the bottom we have u squared. So we're really doing this. If we have integral, this will be u to negative 2 du. Okay. So now when we integrate this, we're going to add 1 to the power. We'll have u to negative 1 over negative 1 plus c. Okay, so that means if we were to plug this back in, the 1 plus x squared, we would have, well, another way to write this, let's do that first. So a u to the negative 1, that would be, and we have the negative 1 on the bottom, so this is going to be negative 1 over u to the positive 1 plus c. Okay, and now plug in the 1 plus x squared, so we have negative 1 over 1 plus x squared plus c. Okay, let's take a look at our next example. So we have integral of ln 3x dx over x. Okay, so what could be our u? Well, looks like ln 3x. So u equals ln 3x. That means du would be du would be 1 over x dx. Okay. So it looks like we have that. Right? The 1 over x dx, that's here. That's our du. And our ln of 3x, that's our u. So we really have the u and the du. So when we integrate this, we have u squared over 2 plus c. Okay, now plug in the ln of 3x again. So this will be ln of 3x. And we're going to have this squared over 2 plus c. Okay, let's take a look at the next one. Okay, integral of x e to the x squared dx. Okay, so let's do our u. Now here, for our u, notice how we have a e to the x squared. And anytime we take the derivative, it'll be e to the x squared. And then we take the derivative of x squared, which is 2x. Now we don't have the 2x, but we do have an x. So that's good that we have the x. We can always work with the missing 2 to compensate it. Okay, and I'll show you what I mean. So to start off, we're going to have u equal to just x squared. And then du would equal 2x dx. Okay. So now notice we don't have the 2x dx. So we're going to do a little manipulating here. We're going to put this right side in the same form as what we have in our problem. We don't have 2x dx, but we have x dx. So the way we get x dx is if we divide both sides by 2. So here on the left, we really have 1/2 du equals x dx. Okay. Okay, so now we're going to plug that in, and we're going to plug in e in, no, we have e, but in place of x squared, we're going to plug in u. So this is going to end up becoming 1/2 e to the u du. Okay, now the 1/2 we could pull outside of the integral. So I'll go down here, 1/2 integral of e to the u du. And now integral of e to the u is e to the u. So this means we end up with 1/2 e to the u plus c. Okay, now plug in the x squared back. So 1/2 e to the x squared plus c. And that would be it. Okay. Alright. Integrate dx over x plus 3. Okay, so we're going to set u equal to x plus 3. Derivative of x would be 1, so we end up with du equal to dx. Right? You could put 1 dx, but basically it's the same as just dx. So when we integrate this, we have u, and then we have du. Okay, so when we integrate this, this will be ln of u plus c, which is ln of x plus 3 plus c. And that would be it. Okay, let's do one with bounds. Okay, evaluate. And it says round to nearest thousand. Okay, so here we have a function. It looks like it's the x squared plus 3 that's underneath the square root. Okay, x squared plus 3. So we're going to set u equal to x squared plus 3. du would be equal to 2x. Now we don't have 2x there, we have a 5x, but that's okay. Right, that's okay. We could get that to easily look like a 5x. Right, so how do we get that to look like a 5x? Let's see. Well, think. And we're going to be ending multiplying by 2. 2 times what would equal 5? Right? If we divide both sides by 2, so 5 halves. Okay, so if we multiply both sides by 5 halves, that's going to get us where we want. Okay, so multiply both sides by 5 halves. So we have 5 halves du would equal, the 2 and the 2 cancel, we have 5x. Okay, so we have integral of 1 to 0. Let's first do just a regular integration, and then we'll worry about the bounds. So we're going to integrate the 5x times the square root of x squared plus 3 dx. Okay, so we have, I'm going to write this like this. I'm going to write the x squared plus 3. Now it's the square root is the same as to the 1/2 power times 5x dx. Don't forget the dx on the 5x. Okay, so now we have, if we're integrating, we have, let's do the u substitution. So we have u to the 1/2 times 5 halves du. Okay, so I could pull the 5 halves on the outside of the integral. So we have 5 halves u to the 1/2 du. Okay, so to integrate this, we're going to add 1 to the 1/2. So it'll be 3 halves. And then we're going to divide by 3 halves. But remember, dividing by 3 halves is the same as multiplying by 2/3. And we still have the 5 halves there. Plus c. Okay, the 2 and the 2 here, they'll cancel. So that leaves us with 5/3 u to the 3 halves plus c. Okay, we could plug in back for our u, the x squared plus 3. So we have 5/3 x squared plus 3 to the 3 halves plus c. Okay, and then it wants us to evaluate from 1 to 0. Alright, so let's do the 5/3 x squared plus 3 to the 3 halves. Evaluate from 1 to 0. So that means we have 5/3 1 squared plus 3 raised to the 3 halves minus 5/3 0 squared plus 3 to the 3 halves. So we have 5/3. 1 squared is 1 plus 3, which is 4. 4 to the 3/2 minus 5/3. 0 squared is 0 plus 3 is 3 to the 3/2. Okay, to make this a little easier, I could pull the 5/3 out. Now I have 4 to the 3/2 minus 3 to the 3/2. And you can do this on the calculator to help yourselves out a little bit. And to the nearest thousandth, we have about 4.673. Okay. And then it says evaluate integral of x over x plus 2. Okay. Assume x plus 2 is greater than 0. Okay. So for our u substitution, we could say that u equals x plus 2. Okay. That's going to take care of the bottom. Now we also have an x on top. But how do we express that x? We could do a little... And we know that, okay, so we know u is x plus 2. That means du will equal 1 dx, or just du equals dx. Now, another way we could get that x, let's do a little, this is a little creative substitution here. If we do minus 2 to both sides, we get u minus 2 equals x. So in place of our top x, we're going to write u minus 2. We'll say u minus 2 over u du. And we'll try to integrate that. Okay. So when we simplify that, keep in mind we could say that this is u over u minus 2 over u. Right, we split apart the fractions. So that means we have 1 minus 2 over u. And now from here we could integrate this, right? Integral of 1 will just turn out to be u minus. And then here this is 2 over u, so this could be 2 over, well, 2 times the ln of u. Plus a constant. Okay, so now when we plug this back in, we're going to plug in the u. U is x plus 2, so we're going to plug in x plus 2 minus 2 ln of x plus 2 plus c. So now here's the one thing that we have to be careful of. Because we can only have one constant, we actually have another constant here, the plus 2. So this plus 2 and this c, let's call this c1. We're going to group those together and we're just going to call it c in general. It's called collecting the constants. So we'll end up with x minus 2 ln of x plus 2. And then this plus 2 and the plus c1, we collect them together and we call it just plus c. And then this will be the final answer. Okay. So that's really it. If you have any questions, just write me an email or bring it up during class. Okay, so keep in mind of the various techniques we used. A lot of times it was the power rule. Sometimes we used the exponential rule with base e. Sometimes we looked at the fraction. We saw it was a natural logarithm rule. And just keep in mind you want to focus on what the function is, what the u is, figure out the du, and then we go from there. Okay? And I'll see you guys in class. Okay, have a good day, have a good night. I'll see you soon.